let's look at a little review of some basics of probability and statistics and introduce what may be a little bit of a new function for you, the Gaussian distribution. So if we start out thinking about basic probability, we can think about a simple die. We've got a six-sided die here. This dice, like any probable event, we can consider that there are n possible outcomes. So for a six-sided die, we have 6 possible outcomes. And we can define a probability P sub j, the probability of some particular outcome j, which is just the number of times that an outcome will occur over the number of repetitions of an experiment. And so if we perform this experiment of rolling a dice an infinite number of times, the limit of number of tries goes to infinity, our probability will be the number of times that we roll, say, a 2 over the total number of tries that we have. And you would expect that, of course, our probability of obtaining any value on this die is between 0 and 1, where 0 indicates that this event will never occur, and 1 would mean this event occurs every time. So we will never roll a 7, but we will always roll a value between 1 and 6. And if we look at some particular value, P sub j, let's say a 2, we expect that we will roll a 2 1/6 of the time. And this brings up a really important idea, the idea of the normalization condition. The normalization condition states that the sum of all possible outcomes, or the sum over all possible outcomes of the probability of that outcome occurring must equal 1. So in other words, there is a 1/6 chance of each of these numbers appearing on the die when we roll it. And so there's a 100% chance, not greater or less than 100% chance, that we will roll one of these values. So this is an idea that we'll use a bunch in this course, quantum mechanics. A few other important concepts that I'll just bring up here. The average, we indicate this with right angle brackets here. So this is average of some value of x. So the sum over all possible outcomes, that value of x for that outcome times the probability of that outcome occurring. Second moment, this is the average of x squared. So this is the value of x squared for a particular outcome j times the probability of that outcome summed over all values. Now the second moment on its own is not super useful. We don't really use the second moment very much, but we do use the variance. And there are a couple of different ways of defining the variance, but we can show that the variance, or sigma squared, is equal to the second moment average of x squared. My handwriting's a little sloppy here, but the squared is inside of that angle bracket, minus the average of x, quantity squared. So you note that these are two different things. This is the second moment minus the average squared. And the variance will always be greater than or equal to 0. The variance also is related to another important concept of the standard deviation. The standard deviation is defined as the square root of the variance. Now let's apply some of these ideas to a Gaussian distribution. You may have heard of a Gaussian before. A Gaussian function is just a constant times an exponential with a squared after the x. So the x term is squared. So c e to the minus x squared over 2a is one way of writing down a Gaussian function. We can draw this Gaussian function. It looks like a bell curve. It's often referred to as a bell curve. And we can define the probability distribution. So the probability of finding some value, the probability of existing at x within some small window dx is then just the Gaussian function times dx. Now let's apply a few of these ideas that we just talked about from our discussion of probability. So we'll start out with normalization. So if we normalize this, right, that's saying that 1 is equal to the sum of all possible outcomes, or in this case, we're going to use an integral because this is defined as a continuum. So the probability and we can substitute in our definition of a Gaussian. Now this integral itself, if we wanted to normalize this, is actually kind of tricky. It involves dummy variables, the way it's typically integrated. It actually typically involves a switch to polar coordinates. It's a bit much to jump into. I mean, it's only a couple of lines. But sometimes when we run into a tricky integral like this, we can use an integral table. And an integral table may sound a little bit old school and dated, but is still actually quite useful. One table that I really highly recommend is the CRC Handbook of Chemistry and Physics. The Chemical Rubber Corporation is what CRC stands for. And if you look at the integral table, these are towards the end of the textbook of the CRC handbook, near the back, and the actual page number depends upon which edition. This CRC handbook is found in the Cooley Science Library or any science library anywhere in the world. It's a pretty useful handbook. And it contains a list of integrals that people have already solved, so you don't have to do all this work yourselves. And so it has in it this integral, e to the minus ax squared, alpha x squared dx is equal to just pi over 4 alpha to the half. And so if we know that this is true, this doesn't look exactly like what we drew above, but it's close enough. And we can first notice that, well, this is an integral from 0 to infinity, and we actually want the integral from negative infinity to infinity. And the reason this is only given from 0 to infinity is that this is an even function, meaning that the left side, x is less than 0, is equal to the right side. And so the integral of the left side is equal to the integral of the right side. And so the integral of the whole thing, we just multiply by 2. So we can rewrite our integral over that full space as 2, and we'll pull out this constant, integral of just half of that space. And if we let alpha equal 1 over 2a squared, then we can write this down as 2c times pi over 4 alpha. Substituting in our definition for alpha. And our normalization condition states that this must be equal to 1. So we can solve for c. C is 1 over 2 pi a squared to the half. And this is what we would call our normalization constant. And normalization constants allow us to use somewhat arbitrary functions like a Gaussian in situations where we want to consider probability, such that the integral over whatever our entire function is still 1. So this has just made our Gaussian much, much more useful. Now, a few of these other concepts, let's think about standard deviation. Gaussians are often used to describe statistics, and we can think about how to get to that standard deviation. And you recall some of the concepts in the standard deviation were the average and the second moment. So let's start out with the average of a Gaussian. The average of a Gaussian, we just indicate with these right angle or these angle brackets, is the sum over all possible outcomes x times the probability of that outcome. And right, we have a continuous function, so we can define this as just an integral. So x times the probability of existing at x. And if we use our now normalized Gaussian, substituting in for c, we can write this down. So this is x times our p of x. And if we were to look at this function, right, this function, if we were to graph it up, would look like this. And things we can think about, our Gaussian was an even function. X is an odd function, right? X just goes to the origin like this. And so the odd function, has the opposite sign on the left and right hand side. And so an odd function times an even function, much like an odd number times an even function, even number, is an odd function. So here's our function. This is odd. The average of an odd function is 0. Now let's look at the second moment next. Now recall the second moment is the average of x squared, and so subbing in our definition for a Gaussian or normalized Gaussian, this becomes x squared times our probability. And again, we kind of want to look this one up in an integral table. This isn't simple like before where we can just say it's an odd function. This is an even function times an even function, a parabola times a Gaussian. And in our CRC handbook, we can find this function, or it's also in your textbook in Math Chapter B. And again, you can just see this is a number, where again, we're using this variable alpha. So plugging in what we found from this integral table with our definition of a Gaussian, we get 2. This is 2 because this integral contains only the half space, whereas here we're considering all of negative infinity to infinity. This just becomes a squared. So our second moment is just a squared. This now allows us to find important things like the variance, average of x squared minus average of x quantity squared. So our second moment was a squared. Our average was 0. So our variance is just a squared. And our standard deviation is just the square root of that. So the standard deviation of a Gaussian is just whatever this term is in our exponential. So hopefully this was a useful reminder of some statistics and probability you knew, maybe a little bit of introduction to some probability you didn't know, as well as a new function Gaussian function.